Welcome back to the class. Let's solve a few more questions from this section. Let's take a problem F1624. Let's take up this problem. The problem says at the instant shown, wheel A rotates with an angular velocity of 6 radian per second. As far as this wheel is concerned, this wheel is fixed at point A. Its center of the wheel is fixed and it's rotating with an angular velocity of 6 radian per second and an angular acceleration of 3 radian per second square. It says determine the angular acceleration of the link BC. How much is the angular acceleration of the link BC and what is the acceleration of point C? What do we mean by the angular acceleration of link BC? You know, as the wheel rotates, this point which was initially here now will reach here, okay? And this point C which initially is here will reach here. So the new position of B and C after some instant of time will be like this. Okay, this is the new position of BC. So what has essentially happened? The link which was horizontal and was subtending no angle with the x-axis all of a sudden has now subtended this much angle with the x-axis. Okay, so it means that link BC is rotating. Once the link is rotating, we are asked how much is its angular acceleration and what is the acceleration of point C. Now, if we are asked to find the acceleration of point C, we have to locate another point. Let's locate point B and write the acceleration equation between point C and point B. But as we write the acceleration of point C is equal to acceleration of point B plus few more terms, we should be knowing at least the acceleration of point B. So the question is, first of all, we should know how much is the acceleration of point B itself. Okay. Now, in order to know the acceleration of point B, we have to find a point in the vicinity of B, okay, with which we will come with, in reference of which we will calculate the acceleration of point B. Let's do one thing. Let's draw a vector from A to B. As we draw the vector from A to B, calculate the acceleration of B with respect to the acceleration of A. And you know, the acceleration of point A is 0. Linear acceleration of point A is 0 because point A is fixed. It is neither moving along x-axis nor along y-axis. So we can write between B and A, acceleration of B is equal to acceleration of A plus angular acceleration of AB, that is alpha AB, cross product with the radius vector from A to B, that is RAB, minus omega square, omega of what? Omega of AB and RAB vector, that is RAB vector is here. Okay, so we can further write this as acceleration of B will come out equal to, since acceleration of A is 0 because A is a fixed point, it does not translate at all, it is just a pin around which the wheel is rotating, so its acceleration is 0. The angular acceleration of AB is given to us. Angular acceleration of AB is the angular acceleration of this wheel, that is 3 radians per second. And if you rotate your if you keep your thumb in this direction, if you keep your fingers in the direction of rotation, the thumb will be along negative k-axis. So its angular acceleration will be minus 3 k cap cross R from A to B, that is 0.2 j cap, that is 0.2 j cap minus omega square. As far as omega is concerned, it is value is 6 square is 36, and RAB vector, as far as RAB vector is concerned, that is 0.2 j cap. Okay, solve this for acceleration of B, we will obtain acceleration of B will come out equal to 3 into 0.2 is 0.6. So this is 0.6. This will be, and k cross j is minus I, minus is plus, so it is 0.6 I cap, and this is 36 into 0.2 is minus 7.2. So this is minus 7.2 j cap. Okay, this is the acceleration of point B. This is the acceleration of point B. Now we will write acceleration of point C in terms of acceleration of point B. So how we will write it? Now the question, again the same problem. As we write the acceleration of C in terms of acceleration of B, in that acceleration equation there will be the term alpha BC, which we have to find, and there will be omega. Okay, there will be omega, angular velocity of BC. So first of all, let's find the angular velocity of BC, and we know in order to find the angular velocity of BC, we should write the velocity equation between B and C. Now, again, how much is the velocity of B first. Let's calculate the velocity of B. Again, in terms of A and B, we can write velocity of B is equal to velocity of A plus angular velocity of AB, angular velocity of AB, cross product with RAB. Okay, cross product with RAB. That's equal to velocity of B will become equal to, in terms of velocity of B, A is at rest, it does not move, it is 0. Omega AB is equal to minus 6k cap. So this is minus 6k cap cross RAB, that's equal to 0.2 j cap. Therefore, velocity of B will become equal, velocity of B becomes equal to k cross j is minus I, minus minus will become plus, so it is 1.2 I cap. Write down the unit, since everything is in meter, so it will be meter per second. So this is velocity of B. Now write the equation of velocity between point B and, write down the equation of velocity between point B and point A. That is, let's now draw the vector from, B to A. As we draw the vector from B to A, let's draw the vector from B to C, sorry, and write down the equation of velocity first. So we'll write velocity of C is equal to velocity of B plus angular velocity of the rod B to C, angular velocity of the vector from B to C or rod B to C cross radius vector from B to C. This is the equation of velocity. Why we are writing the equation of velocity? Because we have to find out the angular velocity. Then we will use it in the acceleration equation. Velocity of C will become equal to velocity of B, which is equal to 1.2 I cap. This is 1.2 I cap. Then we have omega BC. We don't know omega BC, that its magnitude is omega, and it's along, we will write this as omega. We don't know whether it's along minus k cap or plus k cap. We'll write this as omega k cap. Okay, cross RBC, the radius vector from B to C, its magnitude is 0.8 and it's along x-axis, so it will be 0.8. It will be just one place, so it will be along 0.8 I cap. We'll write this as, this is 0.8 I cap. Therefore, velocity of C, as we perform the calculations, will come out equal to, velocity of C will be equal 1.2 I cap. This is 1.2 I cap plus, this is omega into 0.8, that is 0.8 omega, that is 0.8 omega, and omega of BC, which we have to find, 0.8 omega, k cross I is equal to J. Okay, this is VC. So look at the velocity of C. As far as the velocity of C is concerned, velocity of C is in this direction. This is the direction of velocity of C, okay, because it is sliding in this direction. So velocity of C can be resolved into two components. One component will be VC cos 30, another will be VC sin 30 along y-axis. So this VC can be written as, this is VC cos of 30 I cap, VC cos of 30 I cap plus VC sin of 30 I cap, 30 J cap. Okay, this VC is having two components. This is VC cos of 30 I cap. This is VC sin of 30 J cap is equal to 1.2 I cap, 1.2 I cap plus 0.8 omega, 0.8 omega J cap. Okay, let's balance the I and Y component. So we have, when you balance the I and Y components, we have VC cos 30 coming out equal 1.2. Therefore, VC becomes equal to 1.2 divided by cos 30. That is 1.2 divided by cos 30. That comes out equal to, that's equal to 1.385. That's equal to 1.385 meter per second. This is velocity of C. Okay. Now, balancing the J components, we have VC sin 30 is equal to 0.8 omega. It's equal to 0.8 omega. So we know VC is equal to 1.385. Therefore, we can get 1.385 sine of 30 degree divided by 0.8 whole divided by 0.8 is equal to omega. And this omega is of what? This omega is omega BC. Okay, that is angular velocity of the rod BC. I will write here, this is omega BC. And once we perform this calculation, omega BC comes out equal to This is equal 0.865. This is 0.865. This is the value of omega, and the unit of omega is radian per second. Okay. Now we know the value of omega of B and C. Now directly write the acceleration equation. So when we write the acceleration equation, that will be our last step. The acceleration equation is, we will be now writing the acceleration equation between B and C. The acceleration equation now we have, we'll write acceleration of C is equal to acceleration of B plus angular acceleration of BC, that is alpha BC, cross radius vector drawn from B to C, that is RBC, minus omega BC square, which we have calculated 0.865, into radius vector from B to C, that is RBC vector. So acceleration of C, again, acceleration of C is in the same, is in this direction. It can again be resolved into two components, AC cos 30 along x-axis and AC sin 30 along y-axis. So we can write this as, this is AC cos 30 I cap, AC cos 30 I cap, plus AC sin 30 j cap. This is AC sin 30 j cap. AC sin 30 j cap is equal to acceleration of B. As far as the acceleration of B is concerned, we have calculated the acceleration of B, that is 0.6 I cap. Acceleration of B is here, it is 0.6 I cap. So we'll write this as, this is 0.6 I cap, 0.6 I cap minus 7.2 J cap minus 7.2 J cap. This is acceleration of B. And then we have, this is acceleration of B. Then we have plus alpha BC, which we don't know, its magnitude is alpha, let it be along K cap. So we'll write this as alpha K cap. If it's not along K cap, if it's negative along negative K cap, then once we are solving for alpha in next equation, it will come out to be minus. Okay, so this is alpha K cap cross RBC. The radius vector from B to C is 0.8 I cap. This is 0.8 I cap, 0.8 I cap, minus omega BC. Now is omega. We have calculated the value of omega BC. It is 0.865. This is 0.865. And RBC, the radius vector from B to C, is 0.8 I cap. So this is 0.8 I cap. Okay. So now let's solve this. So we have 0.6 I cap. This is 0.6 I cap, 0.6 I cap, minus 7.2 J cap, minus 7.2 J cap. Then we have plus K cross I is equal to J. So this will be 0.8 alpha J cap, 0.8 alpha J cap, minus, this is 0.865 square into 0.8, that is equal to minus, to perform this, it's equal to minus, minus 0.599. It is 0.559 I cap. Okay. So now let's balance the I and J caps to find. So as we balance the I cap, so we have AC cos 30, I cap balancing gives us AC cos 30, equating I component. So it's AC cos 30 becomes equal to, we have a 0.6 I cap, we have 0.6, and we have minus 0.559, minus 0.559. Okay, both are along x-axis. So we have AC cos 30, it is here, is equal to 0.6 I cap minus 0.559 I cap, that's 0.6 minus 0.6 minus 0.559 is equal to 0.011. Therefore, acceleration of C will be equal to 0.011 divided by cos 30, and that is equal to 0.011 that's equal to that's almost equal, it is equal to, just a minute, 0.5 minus 0.1, 0.6 minus 0.559 is equal to 0.01. Okay, this is equal to 0.01. So here will be 0.01 divided by cos 30 comes out equal to 0.01 divided by cos 30 comes out equal to 0.011, and its acceleration, its unit will be meter per second square. So this is acceleration of c. So we had to calculate the acceleration of c, that comes out equal to 0.011 meter per second square. Now we have to calculate the value of alpha. Now let's balance the j components to find the value of alpha. As we are
Sir,
balancing the j components, so there is a little correction here which I have made. Now balancing the j components, we have AC sine 30. As we balance the j components, we have AC sine 30 coming out equal to, we have on the j side we have minus 7.2, we have 0.8 alpha minus 7.2. As we perform this calculation, we know AC value is 0.0011 multiplied by sine of 30 plus 7.2 divided by 0.8 will come out to be the value of, will be the equal value of alpha from this equation. That's equal to, that comes out equal to 0.0011 multiplied by sine 30. So I have sine 30 multiplied by 0.0011, that's equal to 5.5 into 10 raised to power plus, I have to make 7.2, that is 7.200 divided by 0.8, that comes out equal to 9.0006. So the value of alpha in this case comes out equal to 9.0006, that is 9.000 radian per second square. Okay, this completes our question. Our question says find the angular acceleration of the link. Our angular acceleration value is this, it is 9.000 radian per second square, and it was also telling us to calculate the acceleration of c. This is the value of our acceleration of c. Now let's see whether the answers are given correct as per the solution. So this was our problem F1624. So as we go to F1624 section, it is here. Where is F1624? It is here. F1624 is here. Sorry, this is F1624. Let me clear space here with the help of eraser. This is our F1624 solution, and it says the value of alpha comes out equal to, for it the value of alpha, what is the value of alpha? So it's on the next page, F1624. The value of alpha is equal to, yes, it's here. I need to open up this portion. See the value of alpha and check our values. The value of alpha comes out equal to 9 radian per second square, alpha BC. That is in fact our what we have obtained. And the value of acceleration of c is almost equal to 0. Okay, it's writing it's equal to 0, and we know it was 0.0011, which is almost equal to 0. Okay, so we are getting correct answers for this problem as well. This is how students have to solve some more problem. But look at the approach. The approach that has been used by the author in solving this question is, again, this is called the concept of instantaneous center of zero velocity, which we have not discussed yet, which we'll be discussing at the end of the chapter. But whatever concepts we have discussed, that is concept of relative velocity and relative acceleration, we are successful in solving these questions using the concepts we have already discussed in the class. Thank you very much.